Hubhopper Originals.
To start your podcast for free, log on to studio.hubhopper.com.
Hello everyone and welcome back to Indian Genes. We have a very special guest for you today. He's a senior scientist at CALTECH and an observational cosmologist working in the fields of galaxy evolution, cluster cosmology and cosmic backgrounds. He has also been involved in developing the next generation of smaller explorer missions in collaboration with JPL, NASA Jet Propulsion Laboratory. Between 2010 and 2018, he has served as the project scientist and project manager of the US Planck Data Center at CALTECH. The Planck mission was a space observatory operated by the European Space Agency, which mapped the cosmic microwave background at microwave and infrared frequencies. We talked to him about his theory and evidence of parallel universes that exist within our universe's cosmic microwave background. Our guest today has also written numerous science papers on his field of study, and Indian Genes very proudly brings you a very special guest in this extremely interesting conversation with none other than Ranga Ram Chary. So Ranga, from everyone here at Indian Genes and India, a very, very warm welcome to you. Thank you so much for sparing time to talk to us. I know that you are a very busy person, and for all our listeners here, I'd just let you start by giving us a little bit of a brief on where you are currently, what you are involved, and anything interesting that you are currently researching on. So I'll leave that to you.
Right. Thanks very much for having me, Joaquin. It's a pleasure to talk to you and share some of the excitement of astronomy and cosmology with you. I am currently a staff scientist at CALTECH in Pasadena, California, and I work on multiple missions, all of which are aimed in different ways to clarifying our understanding of the universe. Astronomy is a very observational field, so we build telescopes at different wavelengths to collect data, and by analyzing the data, we try to answer questions like, are there other Earths out there? How many galaxies are out there? How did all the galaxies and stars in the universe come about? And what was there right in the beginning when the universe was a baby universe? So, in an attempt to answer these big fundamental questions, we build these telescopes and collect the data. And one telescope doesn't answer these questions. You have to build different telescopes operating at different frequencies or different wavelengths. Some of them operate in the X-ray, some of them operate in the optical wavelengths, some of them even operate at radio wavelengths, which, those who are in India may be familiar with the capabilities of the giant meter wave radio telescope in Pune. So this is why we undertake science. It's or astronomy. We take measurements, and through analyzing these measurements, we try to test a scientific hypothesis. And that's where we're at.
Great. And this interest for you in cosmology or getting into this particular field, how did this start for you? What inspired you to go down this path? Did you always know that this is what you wanted to do as a child, studying and growing up? Or was it something that happened to you and then you realized that, okay, this is what I want to do? That would be interesting to a lot of our listeners, that what got you going on this path?
It was quite a chance entry into astronomy. Living in a big metropolis like Delhi, you don't really get to see the clarity of the night sky. And so you don't really get to see other galaxies out there or star clusters and things that you can see when you go out into really dark spots, because light pollution is killing us in terms of seeing faint things. So where I picked up on astronomy was actually as an undergraduate. I was an computer science and engineering student in Trichy as an undergraduate. And in the course of summer and winter months, I was curious as to how one may apply all the programming skills I was learning. I did not find the programming in itself an interesting challenge. I mean, I found it to basically be a tool, but I wanted to apply that tool to different problems. And so I happened to find a flyer. There was a family member, a sister of mine, who was working at an observatory, and she sent me a booklet, and we looked at the flyer, and I found the kind of research that was going on in that booklet quite fascinating. And when I read that, then I said, oh, this sounds like an interesting field to apply programming skills to. And so I applied to summer and winter research programs at various research facilities just to build my scientific programming skills and applying them to scientific problems. And that's how, then that's what led me to apply in astronomy in grad school. And that's how I got my master's and PhD in that field.
We also know that you were very closely associated with Europe's Planck mission, which was to study the cosmic microwave background, or we call it the relic radiation from the Big Bang. And maybe you want to tell us more about that particular mission and what your findings were through that mission, and then we can take it forward from there.
Right. So the Planck mission was, as you correctly pointed out, indeed to study to measure the cosmic microwave background. It provided the sharpest, clearest view of the cosmic microwave background compared to all other missions in the past. And it was the third generation mission. So the first thing which studied the cosmic microwave background, the first space mission, was actually the COBE mission, which was back in the 80s and 90s. And then there was the Wilkinson Microwave Anisotropy Probe, which was the WMAP, which was in the early 2000s. And then there was Planck, which was in the end of that first decade in the 2000s. And with each successive mission, we've gotten a clearer, sharper picture of the night sky at radio wavelengths. Now, the night sky at radio wavelengths is you can hear or see a lot of things in these through these extremely precise telescopes. First of all, Planck was the coldest thing in space. It was the instruments on Planck had to be cooled to 0.1 degrees above absolute zero.
Wow.
So 0.1, 100 millikelvin, in other words. And the reason you need to cool the instruments down, is because just the vibration of particles, basically electrons, protons, alpha particles, whatever the stuff is made of, just the vibration of that adds noise on the detectors, as the semiconductors. And so to beat down the noise, you have to cool the instrument down to 100 millikelvin using a complex refrigeration system. There was a 3-4 stage refrigeration system. And that allowed us to get the sharpest view of the cosmic microwave background. Now, what is the cosmic microwave background? So the cosmic microwave background, which is also called the CMB, is the relic radiation from the Big Bang. So what is the Big Bang? Well, Big Bang is what we think the universe came out of. So something like the Big Bang happened 13.8 billion years ago, so billion with a B. And at that time, the distances, there were no galaxies, there were no stars, there were no planets, and the space, all of space had been shrunk down to a really tiny point. And you can say, how do we know that? Well, we know that because the distances between galaxies are increasing right now. And they seem to be increasing when we look back in time as well. So if you can imagine, if you and your friend were separated by say 10 meters now, and you and your friend were separated at 4 meters a few minutes ago, that means that your friend is actually moving away from you. So you can imagine, you can extrapolate back in time and then conclude at what point you and your friend were right next to each other. In the same way, the distances between galaxies are increasing, and well, we're increasing at an exponential rate. And so if you fold this back in time, you can calculate the time at which basically all the universe was shrunk to a single point, and that number is effectively 13.8 billion years. So that's the age of the universe. Now, just to give you a context on what 13.8 billion years is that our sun is 4.5 billion years old. So if you our sun basically formed in the latter third of the formation and evolution of the universe. And by studying the properties of this radiation, which Planck, Kobe, and WMAP were able to detect, we can basically conclude what happened between the time of the Big Bang and now. And that's because these photons have to travel all the way through space to get to us. And so they travel through dark matter potential wells, and I'll explain that in a second. And that causes the photons to become slightly cooler. They sometimes interact with hot gas inside galaxy clusters, and that causes the photons to become more energetic. And so if you think about this whole phenomenon, where you are in a planet in the outskirts of a galaxy, and the Big Bang is way back 13.8 billion years ago, you can imagine that all the photons that are getting to you from the Big Bang have gone through all these various interactions. And therefore, there is a signature of the interactions in that radiation. And so by studying the properties of the cosmic microwave background, we can conclude important physical, we can derive physical properties of the universe, which we wouldn't have been able to do otherwise. And so as I started this whole discussion, science is the process of taking a measurement and then testing a hypothesis. So by taking this precise measurement of the cosmic microwave background, we know how much dark matter there is in the universe, which is matter which is not stars, not gas. It's matter which is totally invisible. We know how much dark energy there is in the universe with great precision. We know the rate at which the universe is expanding right now, and therefore we can conclude what the age of the universe is with great precision. And even more importantly, so that's all the dark sector physics that I'm talking about. The process of the interaction of all these photons as it travels to us tells us everything about the intervening matter too. It tells us, when massive galaxy clusters formed. It tells us when supermassive black holes started to basically grow rapidly and put out tons of radiation. So the process of taking these measurements tells us a lot of things about the universe, and which is why we like to take measurements of increasing precision as technology allows.
That's the best explanation for the Big Bang that I've heard, because while you were speaking, I could actually visualize it. And I just want to come back to the Planck mission. Now, you did mention about telescopes earlier, and I know that the Planck mission was sent into space on a rocket. So, do we say that it is probably better for us to get better measurements, that we do not use terrestrial telescopes and we have to get out of the atmosphere for some reason to get better measurements?
Yes, that's an important point. So the Earth's atmosphere, although it protects human life and all life on Earth and allows us to survive here, it basically absorbs some wavelengths. So some of the wavelengths don't even get to the ground. because of the water vapor in the atmosphere or the methane in the atmosphere and so on. And it also adds turbulence. So there's turbulence in the Earth's atmosphere because of the winds, and that causes images to get blurred. And so when you have a telescope on the ground, you're essentially limited to specific wavelengths, and you have to correct for the turbulence in the Earth's atmosphere. Now, the wavelengths that Planck was observing at are partially accessible from the ground, and there are indeed cosmic microwave background telescopes which are in the Atacama in Chile and in the South Pole, which are trying to do these measurements. But what Planck wanted to do was measure the entire sky at 9 different wavelengths or frequencies. And you can imagine that if you're only at one location on Earth, even with the Earth's rotation, it gets very hard to map out the entire sky. You can only see a particular range. If you're in the South Pole, you can only see the southern sky. If you're in the northern hemisphere, you can only see the northern sky. And so if you want to map out the entire sky, you either build 2 telescopes, one in the north, one in the south. But if you also want to observe at certain frequencies which are inaccessible from the ground because of the absorption, then you need to go above the Earth's atmosphere. And so it is for that reason that the Planck and COBE and WMAP and any space mission is actually launched above the Earth's atmosphere, so you're not affected by, 1, the turbulence in the Earth's atmosphere, and 2, the absorption of photons of the Earth's atmosphere, and 3, the fact that the Earth's atmosphere is warm, so it also contributes radiation. So we don't want that to be a source of noise. So if you're trying to make really, really precise measurements, you basically go outside, go above the Earth's atmosphere. And this is why Planck was carried to space, about 1.5 million kilometers in the direction opposite the sun. So you draw a line from the sun to the Earth and extend it 1.5 million kilometers in the opposite direction. And that's roughly where Planck was. That's called the Lagrange point, where the forces of gravity of the sun and Earth balance. And Planck remained in that Lagrange point and, Lagrange region, I should say. The point is where the forces balance, but Planck was not at exactly one point. It was orbiting that point. And in the course of 6 months, it mapped out the entire sky as it was spinning around. And then 6 months later, it mapped out the sky again. So with each mapping out of the entire sky, the quality of our data improved, and we were able to get the highest precision map of the night sky. Now, Planck was an interesting mission because it was a remarkable collaboration between the European Space Agency, which was the lead institution on Planck, and NASA, which is the US side of the European Space Agency, National Aeronautics and Space Administration. And so the technology has gotten so complex that it's very important to have international collaboration such that we can do these complicated things. And so, Planck, the European Space Agency, ESA, provided almost many components, the dominant set of components for the Planck spacecraft, and NASA helped with providing some of the coolers and some of the data reduction techniques and some of the data archives. And so this long extended collaboration, which lasted for more than 2 decades, I think, certainly helped in the success of the Planck mission.
Great, and I think we've all seen those pictures of what Planck was able to map of the entire universe, and I think most of our listeners here who are space enthusiasts have seen that, and it's very interesting to know that you were actually involved in mapping that picture. So that's an amazing fact. And I also know, which I will come back to a little bit later, you spoke about these 9 points. And I know that you have a theory, you've written a paper on it. So that is very interesting on its own. So I would like to come back to that a little bit later. But just to go back to the analogy that you gave earlier about the expanding universe, you mentioned if there are two individuals at a distance of, let's say, 4 meters, and then it extends to 10 meters, that means that that particular person has moved away. Are we, or do we say that both are actually moving away? Because from your point of view, that person is moving away, but there is no central point in the universe. Would that be right? Because
That's
everyone's moving away?
That's correct. You're exactly right. It's basically like the surface of a balloon, just the surface of a balloon. You draw a set of points on it, and you blow up the balloon. Then all 2 points are increasing in separation as you blow it up. So yeah, there is no center of the universe as such. And what's happening is space itself is expanding, which is why the galaxies are moving apart from each other.
So, unfortunately, everything that we hear about individuals or the advice that we get, philosophical advice saying that you are the center of the universe, unfortunately, practically, that's not true.
Yeah. Uh, yeah, that's. I would say that's true. What you just said.
Yes, yeah, yeah. So, when you were mentioning about these or this expansion, and I just want to come back to these anomalies within this expansion in the cosmic wave background, because that would take us to probably one of the most interesting topics that we would want to talk to you about and dive a little bit deeper into is something about the multiverse, like it's called now, or parallel universes. But from a scientific point of view and from observation and data, how did you come to that conclusion? Let's start from there.
Right. So we need some background knowledge on that one. So let's back up a second. And so, as I said, the measurements by Planck give you the highest precision estimates of how much dark matter and dark energy there is. Now, what is dark matter? I said it's absolutely non-luminous matter. It's not stars, it's not galaxies, it's not the gas. It's something whose gravitational influence that we can see because it causes particles to move towards it. But and so we know that it's there, but it's not putting any radiation out by itself. Okay. But then there is this other thing called dark energy. So dark matter makes up about 27% of our universe, and dark energy makes up 73% of our universe. And it's yeah. And so, what is dark energy? So dark energy does exactly the opposite. It's essentially an energy of vacuum, and it's partly responsible. It seems to be everywhere. It seems to be permeating space, and it's partly responsible for the accelerating expansion of the universe as we see it now. And so the probability that we have vacuum energy at roughly 70% is somewhat surprising. It was a wild result which came out in the late 90s by observing exploding stars. But now we think that it's more or less, we're fairly happy with the measurements, and so we think that it does exist. And so the probability that the vacuum energy has the value it has is very, very tiny. It's, the vacuum energy is so much stronger than what we expect that the probability that it has that value is really, really small. And the way to think about this is there are 8 billion people, humans on Earth, and each human is unique in their own way. And so you can say that the probability of finding another human who's identical to you, who has had exactly the same experience as you, is smaller than 1 in 8 billion. In the same way, the probability of this vacuum energy having the value that it has is definitely smaller than 1 in 8 billion, but it's more like 1 in 10 to the power 500 or something. And so that immediately leads to the question, is the vacuum energy just a random number? The vacuum energy that we have, is it just a random number among a whole set of numbers? So if it's 70% of our universe Is it slightly weaker in a different part of space? Is it slightly stronger in another part of space? And so on. And so the multiverse hypothesis is that there are multiple universes out there, and each universe has a slightly different set of physical properties. Is it vacuum energy? Is it the gravitational constant? I couldn't tell you, but it has slightly different physical properties. And the reason that the majority of those properties cause universes to basically fail, in the sense, what is a failed universe? So a failed universe is a universe in which you don't have any stars or galaxies forming. So it either forms and then collapses on itself because of its own energy density, or it expands, and it expands extremely rapidly so that there is no time for stars and galaxies to form. So it's a cold, dark place. And so if you fine tune this vacuum energy to have about the value that we have in our universe, then that causes our universe to last for 13.8 billion years. And as I described earlier, for a sun to form, the universe needs to be the sun formed 4.5 billion years ago, which means that the universe needed to have lasted at least 9.5 billion years for our sun to form. And so if all these other universes, which have different physical properties, don't last for that long, we wouldn't have had our sun form. And so the fine-tuning of parameters to create our universe is what can be construed as the possibility of a multiverse. So maybe there are other universes out there. All of those are failed because they have the wrong physical constants. And so we don't have stars and galaxies form. But in our universe, because we just have the right physical constants, we have life form, and stars form, and planets form, and galaxies form. So that's the multiverse hypothesis. So it's sort of like bubbles in a soda bottle, except each bubble has a different set of physical properties. And we are inside one of those bubbles, and we can only see inside our bubble. So we would never know about the existence of the other bubbles in that soda bottle unless it happened to come into contact with our bubble. And that's the hypothesis we were trying to test with data from the Planck satellite, which is, are we seeing any anomalies in the cosmic microwave background which may be a signature of collisions between bubbles or collisions between alternate universes. And well, it's a very difficult game. It's first of all, you're looking down into the noise, and you have to remove all these other physical signatures that are there. The other galaxies are the other sources which are out there in the sky, and so we do not have unambiguous evidence of such anomalies. We see hints of anomalies, but in science, a hint is not proof of outstanding evidence. We need to be definitively sure, with a high statistical threshold, that we can disprove all the other hypotheses. And so we're not there. And so the point of this whole study was to test the multiverse hypothesis, because, as I said earlier, a scientific study takes measurements to test a scientific hypothesis. If you can't test the hypothesis with the measurement, it's not science. And so by taking the study and studying the properties of the cosmic microwave background, we were trying to see if there are any anomalies that one could attribute to collisions between other universes and ours. And well, we haven't found it, but we're searching hard.
Right, and it throws up amazing possibilities. And you mentioned, or you spoke about fine tuning. Now, for example, within our universe itself, or our observable universe, this fine tuning seems to be really, really interesting, because besides it having to have formed uh, matter and galaxies and stars, it then comes down and has an implication right down to, for example, a solar or a lunar eclipse, because fine tuning also involves the distance of the sun, the amount of oxygen or the amount of carbon dioxide in the atmosphere for life to evolve, because fine tuning also has an impact on life. So there may be other planets where this fine tuning does happen to a particular extent, but it stops the moment it comes to what is required for life. And what do you think about that as to the micro fine tuning within this universe? Is that interesting to you as well?
Yes, that's an excellent question. And you're absolutely right. For life to form, you need fine tuning of conditions. So, for example, in our universe, as far as we know, right now, at the present time, life only exists on Earth, and so that provides a bias onto what kind of life could be out there. So we think it needs to be carbon based. We think it needs to have some sort of liquid water, or at least some kind of organic molecules, complex organic molecules. We also need something called homochirality, which is all the organic compounds are of a particular handedness, which I won't get into in detail, but there are all these requirements to have even simple unicellular life, let alone complex life like us, and the chemical reactions need to have happened at a particular rate to get complex organic molecules to form and keep increasing in complexity. We need, let's think about the simpler big picture things, like we need ozone to protect us from UV radiation. We need water to allow chemical reactions to occur. So all these things, we need energy from the sun, or from the gravitational settling of the Earth, and from radioactivity from the interior of the Earth, which warms the planet. All these seemingly, obvious things are fine tuning in different ways, and the jury is out there that how much fine tuning does it take to get life to form on a planet. And many people have done these experiments, like there was the Miller-Urey experiment, where they stuck together a bunch of organic compounds and they blasted it with effectively lightning and temperature, and tried to make more complex organic molecules. And no, they didn't form life. They formed complex organic molecules, but they definitely didn't form life. So what does it take to form life is a very difficult question. And whether it needs some fine-tuning of various parameters, the jury is out there. I could not answer that question.
Right. And the multiverse, I guess, also tackles the question about what happened before the Big Bang. And would that be accurate to say we then don't have to get into that, because it just is a continuation, like you mentioned about a soda bottle or the bubbles in a bottle? It just could be a bubble coming in and then going out. So there is no definite beginning. There is a definite beginning as far as this universe is concerned. But in the sea of bubbles, we do not need to explain or get into any discussion about what happened before the Big Bang, because what happened before the Big Bang probably would also happen after the Big Bang, and it just all continues.
Yeah, so at some point you lose information, right? There is nothing that you can observe that allows you to test what happened before the Big Bang. There are these models of things called cyclical universes, which says that the universe collapsed and then expanded and collapsed again. And various people have been trying to make observational tests of things like these cyclical universes to see if, say, singularities from which may have been before the Big Bang still persisted after the Big Bang. But all that is a regime of active research, and I would say it's not even mainstream science at the present time, because there is certainly a large fraction of the community that thinks that accessing information from before the Big Bang is almost an untestable hypothesis. And so if it's an untestable hypothesis, it gets pretty tough to even evaluate scientific theories. So yeah, so I would say we don't really know what happened before the Big Bang, or if there was a before the Big Bang. But everything that we observe started at time t equals 0, which was 13.8 billion years ago.
Right. And you did mention that you were studying these anomalies in the microwave radiation. So, is there anything that tells us, or when you come down to any specific anomaly, and you were talking about these 9 points, that there is a possibility of two of these universes actually clashing, interacting, and that could be a sign, or that could be the beginning of something that could later on, as we move into science, we can find a small door there and then push ourselves into that direction?
Yes, right. So it's the method of science. You find an anomaly and then you study those anomalies in greater detail with better data and see if those anomalies are just instrumental noise or they're actually some real anomaly in due to an astrophysical process. And that's exactly right. So we have these anomalies in the Planck maps, which we don't have a better explanation for it. So we said that, those anomalies, we asked the question, are those anomalies testing collisions between bubble universes? And so the thinking is we probably not, but because it's a very statistically low significance detection in a single frequency band, I would say, again, we need a high bar um, to clear to prove that these things are robust, these anomalies are robust. And so ideally, we would get a different instrument to look at the same patches of sky with sharper resolution and sharper and deeper sensitivity, and analyze those data to see if those anomalies persist. But it takes a very long time to design a mission, build it, launch it, and there are other competing interests out there which would like to study things which are in our universe, not necessarily the multiverse hypothesis. So that's not happening anytime soon.
Right. And then sticking to our universe, this is something I always wanted to ask somebody, and I think you're the perfect person for that. We do read a lot in modern literature or on articles that come out about the observable universe. And I just want to understand, what are we supposed to understand when we hear the term observable universe? Is there also a part of the universe that cannot be observed, and so we do not know how large the universe is? How do we, and people who are not really experts in this field, how do we visualize that?
Yeah, what you said is exactly right. The observable universe is a subset of our universe. It's it's essentially a sphere around us, which over 13.8 billion years, the photons can get to us. So if there was a photon which is just outside that sphere, it wouldn't yet have gotten to us. We'd have to wait till tomorrow for that photon to have gotten to us. And so that observable universe is that bubble which which has allowed photons to get to us. And it's a subset of the entire universe. We know for a fact that our universe is larger than the observable universe. But no matter which direction we look in our universe, the cosmic microwave background is isotropic. That means it looks the same regardless if you look north, you look south, you look in this direction, you look in that direction. It looks statistically the same. And that's what allows us to conclude that the entire universe must be about the same. This concept of the universe, the observable universe, being isotropic. So, in other words, you see a part of a tennis ball, and it looks like it's made of yellow felt, and so But therefore, you conclude that every other part of that ball must also be made of yellow felt, although there is the remote possibility that other parts are made of green felt or made of cotton or whatever. But the concept um, because the cosmic microwave background is isotropic and we are not in a special location, argues that what we are seeing within the observable universe is a honest representation of our universe as a whole.
So technically, given enough of time, would where all the photons from 13.5 billion years do reach us, given enough of time for this to play out, we would have mapped, or there would not be any unobservable universe because all the light has reached us? Or would that always be the case because the universe keeps expanding and we'd never reach a stage where all the photons would reach us?
Yes, we would never be able to observe the entire universe because the universe is expanding at an accelerating rate. And so the photons from distant parts of the universe would never get to us because, well, the distances between galaxies are increasing. So, yeah. So the observable universe will always remain a subset of the true universe.
Ranga, a lot of our listeners here are college school students who are in universities and probably thinking about building their careers and moving forward in whichever direction they choose to. So your talk is going to be really inspiring to them, and I'm happy that we could bring this to them. What I also want to know from you is what is what are current areas that interest you and fields that you think are the future of this particular field that you are in. But what I want to get to is what is currently exciting you, and what do you think is where all the information seems to be hidden?
Well, the entire endeavor of science is fascinating. Everything, I mean, astronomy is one end of the spectrum, but um, there is stuff in microbiology, there is stuff in chemistry, there is stuff in neurology. Every field has its unique challenges and problems. And so it's uh, everything in in science, which is effectively a better way of understanding nature, has many unsolved problems. And so, yes, you're right. It's important to know what the big questions are. And to be somewhat practical, I'd say the biggest challenge right now is climate change. Um, it's sort of an existential crisis for humanity as a whole, and so we need to develop technology, or we already have developed technology. We need to adopt technologies which mitigate human carbon footprint, so that we don't end up um, destroying a good fraction of humanity um, and life forms on the planet. So I would say, as a big picture overview, in science, climate change is one of the biggest problems. But in astronomy itself, I mean, it's very hard to predict what will be hot in the next 5 years or next 10 years, because astronomy is a rapidly changing field. And so, for example, 10 years ago, and over the last decade, I should say, one of the most exciting fields has been the study of planets outside our solar system, which is called exoplanets. These were first discovered in the mid 90s, but now with recent NASA missions and ESA missions, we have been able to characterize their atmospheres. We've been able to study what their interiors might be composed of. And so identifying these exoplanets, which may have conditions which are suitable for the formation of life, is definitely one of the hottest topics these days. And that comes with its whole set of questions. Does the planet have an atmosphere? Does the planet have enough liquid water? Does the planet have conditions which are suitable for complex hydrocarbons to form, which may build up into amino acids, and therefore the first bacteria and the first unicellular organism? So that's the sort of questions which are coming up, which are on the interface between biology and astronomy. But in addition, there is a lot of interesting work going on with the launch of the James Webb Space Telescope, which including studying the first galaxies that may have formed after the Big Bang, and basically trying to understand where our galaxy came from. It's also, some of these measurements are going to reveal to us where supermassive black holes came from. So supermassive black holes seem to exist at the centers of massive galaxies. And so, for example, our galaxy has a supermassive black hole in its nucleus. And where do these things come from? And that's one of the unsolved problems in astronomy. So I'm just naming two of almost 40 or 50 topics that I can ramble on, but it's very hard to predict what will be an exciting topic in the future. That's what is currently very exciting.
And when it comes to space exploration and popular culture, what we are bombarded with these days is a lot about travel into space, getting to Mars, fighting the unknown alien invasion, getting prepared to launch satellites with rockets and defense systems into space. But I want to just come back to what you first spoke about, which was global warming and all the effort that we do put into getting to another planet. For example, Mars, I don't think is going to be a very comfortable place anyway. So if we already have a planet and we've already kind of settled down here, if we do put all our resources, energy, intelligence into sorting the problems out on this planet first, there may not necessarily be a need to, in the near future or midterm, think about moving away, because what we do when we move away, if we've not solved the basic problem of how we deal with each other or the way we live with each other, we're going to take that problem to another planet and then want to move from that planet to another planet. So we've not solved the problem. We've just taken the problem into space.
Yes, I agree with that viewpoint. First of all, we have not found a planet which is going to be as conducive as ours for allowing us to survive. Not yet, anyway. I think there is a chance that we may find a planet in the right temperature range with liquid water, with the right atmosphere. I think that's probably not that far in the future. But the distances involved are so large. The nearest star is like 3 light years away. And so um, the probability that we will be able to get there and survive the radiation, as well as all the hardships that one is going to be from being in a confined space for such a long period of time, I don't think that at the present time we are set up to do interstellar travel. At best, and we have obviously been in a space station in low Earth orbit for a very long time now, and that's okay. But even that requires a colossal management process from the surface of our planet, which, frankly, if you were just to leave the astronauts in the space station and cut off all connection with the Earth, that would not go very well. And so we would not want to do that. And so with that thinking and with that viewpoint, we definitely aren't set up to travel and travel to other planets and set up a new base there. So I agree, we should be taking better care of our planet, and understanding that we are a part of a complex ecosystem in which each component serves an essential function, all the way from the tiniest microbe, probably in our human gut, to large elephants and whales. Everything serves a purpose in this complex ecosystem, and not all of it is obvious when we are going about our day-to-day lives.
Right. And you spoke about exoplanets and the discovery of, or the opening up of this new world about exoplanets. And probably before 1995, that was still fringe, and people were not ready to accept the existence of exoplanets or exoplanets. And the moment it did happen, then the floodgates opened, and We are finding an exoplanet every day today. Now, the reason I'm connecting that to today is what we see today. And do you think we are at the cusp of something similar where we need to first detect life? And when I say life, I don't necessarily mean intelligent life. I think it has to be intelligent life because we do not have the capacity to go out there and look for life. So if life is coming to us, it has to be intelligent. And is is this a possibility that we may just be on the verge of detecting something, or once and for all figuring out that no, we are the only living form or living being that occupy our observable universe? What is your take on this? Because as observers and readers from outside the field that you are in, this seems to be a very hot topic at the moment.
I actually have no doubt that on the time scale of decades, we're likely to find microbial life, either buried under the surface of Mars or on Europa or on Titan or one of the moons, or on some asteroid, or in one of these interstellar objects which comes flying through our solar system. So I would not be surprised if through an in situ measurement, and by in situ I mean we go there, we collect a sample, and then we bring it back to Earth and we analyze it, and we see some hints of um, fossilized cellular organisms in that. So I would be very surprised if that does not happen on the time scale of decades. Um, but that's not intelligent life. And you were asking about intelligent life. I think the probability, and one could ask the question, what do you mean by intelligent life? Do you mean technologically complex organisms? And I think the probability, again, it becomes a probability argument. I think all the conditions that need to happen to have a technologically advanced civilization, if you multiply all the factors together, I think the probability becomes so small and the distances involved become so large that I find it hard to believe that we would be able to see signatures of an intelligent life form um, at any point.
And when we talk about moving forward in space or moving forward in science, I know you've got your time is limited, and I'm pushing the envelope here. But if you could tell us, what are you currently working on, and is there anything that you think you want to share with us that you personally have been observing, or some kind of advice? First of all, what you currently are working on, and then some kind of advice to a lot of our listeners here who have not yet made up their minds in which direction they want to go.
Yeah, so again, the way science works, all astronomers are divided among multiple projects, and the big ones that I'm currently working on at this very moment are a project called Euclid, which is to characterize the nature of this dark energy, and that's going to be launched next year, hopefully. Um, and That's one of the big missions that I'm working on. It's led by the European Space Agency, but it has a significant contribution from NASA. In that way, it's similar to Planck in its setup. And so but we aren't yet taking data. That mission has been built and it's about to be launched. What I have data on, and we are analyzing in some detail, is we're trying to study exoplanets. Specifically, we are trying to uh, observe the change in the orbital period of exoplanets, and using that to infer properties about the interior of exoplanets. So by what I mean by all that is, the Earth orbits around the sun once a year, but for some of these exoplanets, if one orbit is 1 year, the next orbit is 0.999 years. The orbit after that is or a few orbits after that, it's 0.998 years, and so on and so forth. So its orbital period is decreasing and we think that this is because the planet is gradually migrating in to the star. And so we're taking these measurements to understand the rate of migration and what that tells us about the interior of the exoplanets. So in some ways, it's the field of exogeology, if you will. The other topic that I'm working on is at the other end of the spectrum, which is we're studying these extremely distant galaxies. And we've known about these galaxies like this one for a while, since the Spitzer Space Telescope was launched about 20 years ago. And they have all the signatures of being the most distant galaxies in our universe. But when you study them in some detail, it seems that there is a lot of dust in them. And the dust is what is causing them to behave like the most distant galaxies in our universe. So we're trying to understand the properties of these galaxies better so that we can avoid being confused by them as we try to understand how the first galaxies in the universe came about.
Very interesting. And you mentioned about exogeology, and just a question about our Earth itself. Do we also, or have we detected any deviation or reduction in our orbit around the sun? Because I guess ultimately that's our fate as well. Or is it that the sun would expand before we can actually move into the sun? How does that end?
Yeah. So any change in the orbit of the Earth is tiny compared, or negligibly small compared to these other planets that we're looking at. But what will happen in 4.5 billion years is the sun will run out of hydrogen and will gradually expand until it becomes something like a red giant star. And it's called the red giant because it's cooler than the current sun and much, much larger than the current sun. In fact, it'll be so large that it'll be about the same size as the orbit of the Earth around the sun. And that's the point at which the inner parts of the solar system become unstable. But this is 4.5 billion years away in the future. And I think, at least for humanity, we have much more immediate problems on that
Yeah.
than that.
Yeah. And we now know the age of the sun. So that's 9 billion then from birth to end, right? Because
Yes.
you said it's
Yes.
4.5 billion ago, and you say 4.5 billion from now, that's the end. So
Yes.
that's an interesting fact, that the sun is going to live a life of 9 billion years.
Yep. 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 That's right.
And before we let you go, once again, I would really want to thank you for this. We've tried this, I think, last week, and unfortunately, due to some technical issue from my end, we couldn't get it going. But you were really nice. You spoke to us. You decided to come back and reschedule this. So first of all, I want to thank you from on behalf of all our listeners and everybody who's tuned in today, but also for the fact that I think you were very eloquent and you were able to very easily simplify what a lot of us would have found confusing otherwise. So I would have loved to be a student in your lecture, definitely.
Well, thanks very much for having me. It was nice to share some of the excitement of science with you. And if there's one thing I would tell everyone, which is ask difficult questions and take the measurements to try to answer those difficult questions, because that's the way progress is made.
Great. And just in case somebody is trying to find or wants to read a little bit more about your work or wants to get in, look at your papers, and that those papers could help them in their research, is there some place that they can find you, or would you want to refer somebody to a link that you have?
Yeah, the astronomy community is very savvy in having all the published journals online. So pretty much anybody can access any scientific paper if they have an internet connection. So the two most common repositories are something called Archive, ARXIV, and the Astrophysics Data Service, Abstract Service, ADS, ABS. And that those two are the places where you can search for papers by pretty much anyone on any topic, and they will allow you to access all that information.
Great. And Ranga, before we let you go, I do know that in your spare time, you either like scuba diving or mountain climbing. Those are two extreme sports, one right to the bottom of the earth and the other to the top of it. And have you been able to do any of that recently?
Well, the pandemic sort of messed up the travel plans, to be honest. But yes, we do enjoy scuba diving. As you know, 70% of the Earth is covered with water, and scuba diving is one of the best ways through which you can even appreciate the underwater world. And so, yeah, there are many fine places out there where one can appreciate the underwater world, including near India. You can go to the Lakshadweep, or you can go to Andaman and Nicobar, or you could go to the Maldives. And if you're a good swimmer, it's pretty easy to get your scuba diving certification. And if you're into climbing and you're reaching, extending yourself physically to reach the high peaks where there is not very much oxygen up in the upper atmosphere, well, India has the Himalayas as well. So get out there and hope that provides you impetus to go and appreciate nature.
Great. Unfortunately, Ranga, I'm not a very good swimmer and I'm a bit afraid of heights. So I'm in the middle. I'll have to find something in the middle. I can't get into any of those two. But once again, from everyone here in India, it's been a real pleasure speaking to you. And we just hope if in future we would want you to come back and talk to us about something new or any of the new discoveries, anything new that you are working on. I just hope you would like to come back and talk to us again.
Yes, it'll be a pleasure. I'll be happy to share the excitement of science with you.
Thank you so much, Ranga.
इस हब हॉपर ओरिजिनल को सुनने के लिए आपका शुक्रिया। अगर आप भी अपना पॉडकास्ट लॉन्च करना चाहते हैं तो हब हॉपर स्टूडियो वेबसाइट पे रजिस्टर करें और 1 मिनट के अंदर अंदर अपना खुद का पॉडकास्ट लॉन्च करें। यही नहीं, स्टूडियो देता है आपको पूरी आजादी कहीं भी कभी भी अपना पॉडकास्ट लॉन्च करने की, सिर्फ 3 आसान स्टेप्स में। तो साथ में अपना पॉडकास्ट शुरू करने के लिए तैयार? जस्ट हॉप ऑन हब हॉपर, सिंपली कंटेंट।